Hi everyone, and welcome to our daily booster for chemistry. This is number 7, and what we're going to be doing today is a topic that is listed on both the foundation and higher tier chemistry advanced information topic list. We're going to be having a look at carbon in all its wonderful forms. So first thing, let's have a look at carbon as an element. It is in group 4. That means it has 4 electrons in its outer shell. Because it has 4 electrons in the outer shell, that means it can form 4 covalent bonds. Now, those covalent bonds could be formed either with other carbon atoms or with other elements. What we're going to focus on in this booster is basically carbon atoms forming bonds with other carbon atoms. We're going to be looking at what we refer to as allotropes of carbon. Now, an allotrope, quite simply, are different forms of the same element in the same state, but with different atomic arrangements. So what we mean by that is we're going to be having a look at carbon in the solid state, but how the carbon atoms have all joined together is going to be different to make these different chemicals that we know and love. The first one is diamond. Now, diamond itself only made of carbon atoms, and the general shape you can see in the bottom left corner there is kind of like a sort of triangle shape. So if you see something triangular shaped, it's going to be diamond we are talking about here. The kind of structure we refer to diamond as having is a giant covalent structure, and in there what we find is each carbon atom is joined on to 4 other carbon atoms. What that means is we get some very distinctive properties about diamond. The first is that it's got a very high melting point and it's very hard. And the reason for those is that it's got a large number of covalent bonds, and in order to break those covalent bonds, we need a lot of energy. So if ever you see a question that says, why does this substance have a high melting point? Then it's got a large number of covalent bonds, or many covalent bonds, which require a lot of energy to be broken. So make sure you've got those 2 parts to it, many covalent bonds, and then follow it up with they need a lot of energy to break. The second property we're going to focus on is its ability to conduct electricity, and diamond does not conduct electricity. The reason for this is that those 4 electrons in its outer shell are all involved in making covalent bonds because it joins the 4 other carbon atoms. So because all 4 of those electrons are involved in a covalent bond, we have no delocalized electrons. As a result, diamond does not conduct electricity. Allotrope number 2 is graphite. Graphite is again a giant covalent structure, but this time our carbon atoms are only bonded to 3 other carbon atoms. This means we have 1 electron per carbon atom going spare, and that electron becomes delocalized. So, properties of our graphite. First of all, it's got a high melting point because there are many covalent bonds which require a lot of energy to be broken. Same answer as we gave for diamond. Second feature here is that our graphite is slippery. Now, graphite is the stuff we find in pencil leads. This is not actually lead, it's graphite. And what you find is when you draw a pencil across a bit of paper, you leave a mark on it. And that's actually a little bit of graphite that you've transferred from the pencil onto the bit of paper. The reason that works is our graphite itself is made up of these little sheets that are all just connected to one another by these little dotty lines here, which are weak intermolecular forces. So we've got these weak forces between the layers, and as a result of that, when we apply the pressure and the force to drag the pencil across the bit of paper, that's enough to overcome those forces and therefore transfer one of those sheets onto the bit of paper. The next one is graphene. Now, graphene basically resembles a single layer of graphite. What we find then is each carbon atom still bonded to 3 other carbon atoms, but they're not having those different layers held together by those weak forces. Instead, it's just a single layer of those carbon atoms bonded to 3 others. What we find is it still has that very high strength because of all those covalent bonds that require a lot of energy to break them. It will still conduct electricity because we still have a delocalized electron. Just remember that one, because any time it asks why a particular material can conduct electricity, it has delocalized electrons is always a good answer to give. And because it's only this single layer of carbon thick, basically it's almost transparent. And this is something they're quite excited in terms of potential future tech uses, because we might be able to do things like make mobile phone screens out of it, make these amazing batteries that charge up in virtually no time whatsoever. So graphene is a material to watch. The last little category that we're going to look at with regards to our carbon allotropes are fullerenes. Now, fullerenes are basically a family of these carbon allotropes that have been designed to be shaped either like tubes or like balls. If we've got one that's designed as a tube, we can refer to this as a nanotube, because what we've done to all intents and purposes is taken a sheet of graphene and rolled it up to make a tube-like shape, kind of like a straw. Now, these nanotubes are incredibly useful to us when we want to reinforce materials, so make them stronger. And the best example is in tennis rackets, because they're incredibly small, hence nanotubes, but they are very strong for their size. So it reinforces tennis rackets, making them less likely to break when you're using them. The second one, the sphere-shaped one, this is a buckyball. Now, buckyball, perfectly acceptable term to use on your exam paper, is made of 60 carbon atoms all joined together in that sphere shape. And this is quite important because we could potentially use these buckyballs for lubricants, first of all, but also, perhaps more excitingly, as drug delivery systems. Because what we could do is we can actually enclose certain drug molecules within that little sphere, and then we could deliver it to specific regions of the body. So if we could find a way to do that effectively, we may well be able to get rid of certain side effects of some drugs. Because what we find is there are some drugs that we take for treating certain illnesses, such as cancers, for example, that have quite wide-reaching side effects because they're affecting all the different parts of the body they're circulating through. If we could have a way to encapsulate that drug within this little buckyball and deliver it only to the cells we want to affect, we're going to get rid of those side effects. So quite an exciting thing if we can get it up and running properly. Final thing to do for today then is head on over and have a go at today's quiz. You can find the link in the description box below. And of course, don't forget to join us again tomorrow for our next Daily Booster for chemistry.